Pliosaurus, the first great giant predator of the seas. When one speaks of the great marine dinosaurs, one of the names that always appears in the foreground is Pliosaurus. Strictly speaking, it was not a dinosaur, but a late Jurassic marine plesiosaurian reptile, yet for popular purposes it fulfilled exactly the role the public imagines. That of a gigantic super-predator that dominated the seas long before forms such as the Mosasaur existed. Its record is concentrated in rocks from the Kimmeridgian to Tithonian about 155 million years ago, mainly in Western Europe and Patagonia. Pliosaurus belonged to the pliosauromorph morphology, composed of a large head, a short neck, a robust body, and 4 limbs transformed into flippers. It was the functional opposite of the extremely long-necked plesiosaurs such as the elasmosaurids. In the best-known species, such as P. funcae and P. cavani, the skull exceeded 2 meters in length, with long and robust jaws, and the total length of the animal is estimated at around 10 meters, with some remains suggesting individuals that approached or even exceeded 11 meters. One of the most distinctive features of Pliosaurus were its trihedral teeth. They were not round in section, but had 3 well-defined faces forming a kind of prism. That trihedral section, combined with grooves in the enamel, is a diagnostic trait of the genus and is present both in European species and in the South American ones. Those teeth indicate that it was not a simple swallower of small prey, but a hunter specialized in large and robust prey, other marine reptiles, large bony fish, and possibly even primitive sharks. The jaw, short in the region of the symphysis but very solid, reinforced that function of a grip bite capable of holding bodies that struggled violently. In anatomical terms, Pliosaurus presents a torpedo-shaped body with a barrel-shaped trunk and a relatively short tail. The 4 limbs are transformed into large and flat flippers, used synchronously in a swimming style that has been compared to the flapping of wings underwater. The reconstruction of species such as P. carpenteri, based on fairly complete skeletons, shows proportions in which the 4 flippers are slightly longer than the hind ones and can easily exceed 2 meters in span. It did not propel itself only with the tail like a crocodile, but with a system of 4 oars that gave it maneuverability and acceleration, ideal for ambushing prey in relatively shallow seas. The environment where Pliosaurus lived was that of the Jurassic epicontinental seas. In what is now southern England, the famous Kimmeridge clay records a warm, relatively deep sea where ammonites, belemnites, bony fish, sharks, and other smaller plesiosaurs coexisted. There, Pliosaurus occupied the top of the food chain. In the southern hemisphere, in the Vaca Muerta formation of Neuquén, Argentina, species such as P. patagonicus show that animals with the same anatomy and function also dominated the marine basins linked to the ancient Tethys Ocean and the Proto-Pacific. The detailed study of jaws and vertebrae of Pliosaurus has made it possible to correct several exaggerations of size that circulated in the 2000s. The famous Predator X, discovered in Svalbard and later described as Pliosaurus funcae, was initially presented with lengths of up to 15 meters and masses comparable to those of a humpback whale. Later revisions, based on more systematic comparisons with other species and on more realistic proportions of the skeleton, reduced those estimates to ranges of 10 meters, still imposing but scientifically more solid. Despite its media fame, the record of Pliosaurus remains fragmentary. Many species historically assigned to the genus have been rearranged, merged, or discarded after recent revisions. Currently, studies recognize a limited number of valid species in Europe and 2 species described in Patagonia, and emphasize that there is a hidden diversity that will probably be clarified with new findings. From a biological point of view, Pliosaurus was a fully marine reptile. Like other plesiosaurs, it almost certainly gave birth to live young in the water, rather than laying eggs on land, a conclusion supported by plesiosaur fossils with embryos preserved in their body cavity. Its lifestyle involved long movements in search of prey-rich areas, perhaps following fish migrations or concentrations of cephalopods with a metabolism that was probably higher than that of a typical modern reptile, approaching an activity regime comparable to that of seabirds or aquatic mammals. In the context of marine gigantism, Pliosaurus represents a first generation of predatory colossi. It demonstrates that marine vertebrates had already explored sizes exceeding 10 meters in the Jurassic, long before the appearance of the great Cretaceous mosasaurs. Its combination of massive skull, specialized dentition, and powerful locomotion defines a super-predator model that would later be replaced but not exactly equaled by other lineages. Kronosaurus, the Cretaceous heir of the giant pliosaurs. At the opening of the early Cretaceous, the role of great predator of the seas that Pliosaurus had occupied in the Jurassic passed into the hands of another pliosaurid of similar proportions. Kronosaurus, a short-necked marine reptile with an enormous head belonging to the same general lineage of the pliosaurs, which inhabited warm and shallow seas in what is now Queensland, Australia, and the northwestern margin of Gondwana, represented by Colombia. Its fossils come mainly from Aptian to Albian rocks, with approximate ages between 125 and 100 million years. The name Kronosaurus queenslandicus was originally applied to fragmentary remains found in Australia at the beginning of the 20th century. Decades later, an expedition from the Harvard Museum of Comparative Zoology recovered a much more complete skeleton, which ended up mounted in a monumental display case in Cambridge. That mount, almost 13 meters long, impressed the public for generations and helped fix the image of Kronosaurus as a colossal monster. However, later studies showed that the skeleton had been reconstructed with too many plaster vertebrae, inflating its real length. Modern estimates placed this pliosaur at around 10 meters, with some specimens perhaps slightly above that figure. The anatomy of Kronosaurus followed the classic pattern of giant pliosaurs. It had a massive skull with a long and deep jaw armed with conical teeth up to about 30 centimeters in length in the largest specimens. That dentition, robust and slightly compressed, was designed to grasp and tear bulky prey rather than to cut it cleanly. The muscle insertions in the posterior region of the skull indicate powerful jaw musculature, capable of generating a bite comparable in terms of relative force to that of large modern marine predators. The neck was very short compared to that of long-necked plesiosaurs. That reduction increased the stability of the skull during attack. The trunk showed robust ribs and a wide rib cage, while the tail, relatively short, played a lesser role in propulsion than in reptiles such as crocodiles. The forelimbs were transformed into broad flippers, with flattened phalanges that formed true bony paddles. It swam by a coordinated beating of the four flippers in a style of locomotion that some studies compared to the underwater flight of turtles and penguins, but multiplied by the mass of several tons. The environments in which Kronosaurus lived corresponded to epicontinental seas and shallow basins connected to the global ocean. In Australia, the Toolabuk Formation recorded an inland sea rich in bony fish, sharks, ammonites, and long-necked plesiosaurs. In that ecosystem, Kronosaurus occupied the role of apex superpredator, without comparable rivals in size within its own group. Circular and deep bite marks found on skulls of Australian elasmosaurids were attributed to attacks by pliosaurs of the Kronosaurus type, which reinforced the idea that it preyed on other marine reptiles in addition to fish. In Colombia, an almost complete skeleton from the region of Villa de Leyva, popularly known as El Fossil, was interpreted for decades as Kronosaurus boyacensis. Recent studies, however, revised that material and separated it into a new genus, Monchirosaurus, although its general appearance and ecological function remained those of a large Aptian predatory pliosaur. That taxonomic debate illustrated the extent to which Kronosaurus functioned as a catch-all for several large early Cretaceous pliosaurs and how modern paleontology tended to better delimit which remains really belonged to that genus. Even the very name Kronosaurus underwent a profound revision. A paper published in 2022 proposed that the Australian holotype lacked clear diagnostic features and that therefore the genus should be considered a nomen dubium, reassigning several emblematic skeletons to another new genus, Ichthyosaurus. Subsequent research did not fully accept that reassignment and defended maintaining, at least provisionally, the combined use Kronosaurus Ichthyosaurus for the set of materials. Beyond terminology, the consensus remained that those pliosaurs represented the same general type of giant predator, with maximum sizes somewhat above 10 meters. As for its biology, everything indicates that Kronosaurus was a fully marine reptile which did not return to land to reproduce. By analogy with other plesiosaurs in which embryos were found inside the body, specialists considered it very likely that it was viviparous, giving birth in the open sea. Its physiology, although difficult to determine precisely, must have been situated at an intermediate point between the metabolism of modern reptiles and that of marine mammals, with a high level of activity that allowed it to carry out long pursuits and extensive journeys between feeding areas. Kronosaurus occupied for millions of years the top of entire food chains in the southern hemisphere, before the rise of other groups such as specialized elasmosaurids and later mosasaurs once again modified the balance of power in the oceans. Nothosaurus, the false lizard that paved the way for marine reptiles. Long before giant pliosaurs like Pliosaurus and Kronosaurus dominated the Jurassic and Cretaceous oceans, the Triassic seas were populated by more primitive semi-aquatic forms that represented the first steps in the conquest of the marine environment by reptiles. Among them, Nothosaurus stood out, whose name means false lizard. It lived approximately 240 million years ago, from the Middle Triassic to the Late Triassic, in seas that bathed the coasts of the supercontinent Pangaea. Nothosaurus did not reach the extreme lengths of later giants, but some large species, such as Nothosaurus giganteus, approached 5 meters in length, becoming important predators within Triassic coastal ecosystems. Its body showed a combination of terrestrial and aquatic traits: elongated trunk, relatively long neck, narrow head, and limbs that still retained a bone structure similar to that of a terrestrial reptile, although with elongated digits likely connected by membranes. That anatomy evoked the silhouette of a cross between a large lizard and an otter, adapted for swimming but still capable of moving, at least clumsily, on land. The skull of Nothosaurus was elongated and low, with a row of long, pointed teeth that protruded even when the mouth was closed. These teeth formed a sort of perfect cage for catching slippery prey. The nostrils were located on the top of the snout, suggesting that it partially raised its head to breathe, similar to a seal or a crocodile. In several skulls, more robust teeth are observed at the back of the mouth, interpreted as an adaptation to grasp and crush thick-scaled fish or hard-shelled crustaceans. Nothosaurus fossil sites are distributed across a wide geographic range, from Central Europe to China and the Middle East, indicating that it occupied an extensive coastal belt along the ancient Tethys Ocean. The sediments where its fossils appear correspond to coastal lagoon, shallow platform, and protected bay environments, with mixtures of limestone and marl recording relatively calm marine conditions. These environments, rich in fish and other vertebrates, offered an ideal scenario for a medium-sized predator that hunted by ambushing in shallow waters. In terms of locomotion, Nothosaurus represented an intermediate stage between terrestrial reptiles and fully aquatic plesiosaurs. It swam mainly with lateral movements of the body and tail, in the style of a crocodile, but assisted by its limbs, which functioned as oars. The arm and leg bones show joints still relatively mobile, capable of supporting some weight on land, suggesting that Nothosaurus could drag itself onto beaches or sandbanks to rest, thermoregulate, or reproduce. However, its lightweight skeleton, with vertebrae and ribs adapted for buoyancy, indicates that its maximum performance was achieved in water. Ecologically, Nothosaurus was an opportunistic predator. Direct stomach contents are scarce, but the shape of its teeth and the faunal context allow inference of a diet based on fish, cephalopods, and small marine vertebrates. Some paleontologists have proposed that it adopted a strategy similar to that of a marine crocodile, remaining partially hidden near the bottom or among coastal structures and launching quick attacks on approaching schools of fish. In shallow waters, its elongated body and relatively flexible neck allowed it to reach prey with sudden head movements. The diversity of Nothosaurus was remarkable. The genus includes multiple described species, differentiated by size, skull shape, and dentition. Some, smaller in size, barely exceeded 1 meter in length and perhaps occupied niches similar to those of small coastal predators. Others, like N. giganteus, represented the upper range, approaching the size of future medium-necked plesiosaurs. That internal variation indicates that the Nothosaur body type functioned well in diverse ecological contexts and that the lineage had time to experiment with different degrees of adaptation to the marine environment. Evolutionarily, Nothosaurus belonged to the group Sauropterygia, the same large lineage that later gave rise to classical plesiosaurs. Many specialists consider Nothosaurs as basal forms, that is, early branches of that lineage that had not yet developed paddle-shaped flippers or the extremely long necks of elasmosaurids. From this perspective, Nothosaurus represented an early experiment in the transition from a coastal reptile to a fully marine reptile. Its mix of traits, such as jaws adapted to catch fish, still articulated limbs, and probable ability to venture onto land illustrated the intermediate steps before the emergence of the true marine dinosaurs of popular imagination. Reproduction in Nothosaurus remains a debated point. Unlike some later plesiosaurs in which embryos were found inside the body, there is no direct evidence of viviparity. Therefore, many researchers have suggested that it still depended on laying eggs on land like modern sea turtles. That hypothesis fits with its limbs still relatively functional on land. If so, the life cycle of Nothosaurus would have involved periodic movements to beaches or islands where females deposited eggs that incubated out of water. In the history of marine gigantism, the importance of Nothosaurus did not lie so much in its absolute size as in its role as a precursor. It showed that reptiles could effectively exploit the resources of coastal seas, developing hydrodynamic bodies, specialized dentition for catching fish, and semi-aquatic behaviors. On that basis, during the Jurassic and Cretaceous, other sauropterygian groups took ocean adaptation to its logical extreme: exaggerated necks, rigid flippers, heavy bodies, and a fully pelagic lifestyle. Styxosaurus, the endless neck of the western interior sea. Among the great marine dinosaurs of popular imagination, Styxosaurus represented one of the most extreme versions of the long-necked plesiosaur. It was an elasmosaurid from the late Cretaceous, known mainly from North America, which lived in the waters of the western interior sea around 80 million years ago. Its fossils came primarily from the Niobrara, Pierre, and Graneros shale formations in what is now Kansas, Nebraska, and South Dakota. The name Styxosaurus referred directly to the river Styx of Greek mythology. The choice was intentional. The holotype of the type species, Styxosaurus snowii, was found near Hell Creek, Kansas, and the name combined that allusion to hell with the Greek term sauros. The first specimen, originally described by Williston at the end of the 19th century under other genera, included a complete skull and more than 20 cervical vertebrae. Only in 1943 did Wells establish the genus Styxosaurus as such. Later, other species were added, such as S. browni, and in 2023 S. rezati was described from Cenomanian material from Nebraska previously assigned to Thalassomedon. In terms of size, Styxosaurus fully qualified as a giant. A reference specimen of S. snowii reached an estimated total length of 10.5 meters, with a neck around 5.2 meters, approximately half the body length from snout to tail. That neck was composed of dozens of cervical vertebrae. In some related elasmosaurids, up to 75 have been counted, making these reptiles true specialists in hyper-elongated necks among marine vertebrates. The anatomy of Styxosaurus followed the general elasmosaurid pattern: relatively small head, very long neck, compact barrel-shaped trunk, short tail, and 4 large paddle-shaped flippers. The skull, though small relative to the body, had jaws armed with conical, sharp teeth adapted to pierce and hold slippery prey. The teeth interlocked when the mouth closed, forming a sort of cage that prevented fish and cephalopods from escaping once caught. One of the most famous Styxosaurus specimens, mounted at the Museum of Geology of the South Dakota School of Mines, preserved much of the axial skeleton and allowed a fairly complete reconstruction of its appearance. The mount showed how the neck curved in a long, continuous arc, although later biomechanical studies indicated that such a position, with the head raised at an extreme angle, would have been physically unrealistic in life. The cervical vertebrae, though numerous, were designed for relatively limited vertical flexion. The neck functioned better as a horizontal structure, extended in the plane of the body. The abdominal contents of this specimen provided one of the most important insights into Styxosaurus biology. About 250 gastroliths, polished stones interpreted as stomach stones, were found in the thoracic cavity. Among them appeared crushed fragments of fish bones. This combination indicated that the gastroliths were not only ballast, but served as a gastric mill, helping to grind prey swallowed whole. The total weight of the stones represented less than 1% of the estimated body mass, too little to act as significant ballast, reinforcing this functional interpretation. Ecologically, Styxosaurus occupied a niche as a predator of medium-sized fish and cephalopods in the western interior sea. This sea, which divided North America into two continental land masses during much of the late Cretaceous, hosted a highly diverse marine vertebrate fauna: bony fish such as Gillicus, lamniform sharks like Cretoxyrhina, other pliosaurs and Mosasaurus. In this context, Styxosaurus likely used its long neck to bring the head close to prey schools without moving the trunk excessively, reducing turbulence and increasing ambush efficiency. The dentition and skull structure suggest that Styxosaurus did not slice its food but swallowed prey whole. The conical teeth, without marked cutting edges, and the relative lightness of the skull were consistent with quickly capturing fish, belemnites, and squid. The neck, although long, would not have been particularly flexible in all planes. Its function would have been to present the head in different positions within a relatively wide volume around the body, rather than perform extreme serpentine movements. Taxonomically, Styxosaurus belonged to Elasmosauridae, occupying a position close to classical forms like Elasmosaurus platyurus. Revision after revision, the genus helped clarify the true diversity of elasmosaurids from the interior sea. For example, materials previously assigned to Hydralmosaurus were reassigned to Styxosaurus after detailed analyses of cervical vertebrae, which showed features unique to the elasmosaurids of that basin. These studies helped better understand how hyper-elongated necks evolved throughout the Cretaceous, from forms with fewer vertebrae to specialists like Styxosaurus. In terms of general biology, Styxosaurus shared traits with other advanced plesiosaurs: full adaptation to the marine environment, locomotion based on the coordinated beating of all four flippers, and probable viviparity inferred by analogy with plesiosaurs in which embryos were preserved inside the body. Its metabolism would have been relatively high, compatible with a life of constant activity in open waters and migrations within the interior sea. The discovery of remains alongside shark and mosasaur teeth suggested that, despite its size, it could occasionally have been prey for even larger predators. Styxosaurus represented the culmination of the extreme neck strategy among sauropterygians. While pliosaurs like Pliosaurus and Kronosaurus opted for huge heads and short necks to attack large prey, elasmosaurids like Styxosaurus invested in neck length to exploit schools of smaller prey with precision and reach. Albertonectes, the longest neck of the Cretaceous seas. Among all known marine reptiles, few pushed the long neck strategy as far as Albertonectes, a late Cretaceous elasmosaurid that inhabited the northern part of the western interior sea in what is now southern Alberta, Canada, around 73.5 million years ago during the Campanian. The only well-documented specimen, Albertonectes van der Velde, was discovered in 2007 in an amylite mine near Lethbridge within the Bearpaw Formation and formally described in 2012. The skeleton was exceptionally complete from the atlas to the tip of the tail, though it lacked the skull. This preservation allowed fairly precise estimates of its size, a total length of about 12 meters, of which approximately 7 meters corresponded solely to the neck. Relatively, nearly two-thirds of the body length was concentrated in front of the trunk. The most striking feature of Albertonectes was precisely this disproportionate neck. It had 76 cervical vertebrae, the highest number known in any vertebrate, surpassing even other extreme elasmosaurids such as Elasmosaurus or Styxosaurus. In dorsal view, the cervical series formed a column of relatively low, elongated elements, with articular surfaces adapted for wide but not exaggerated movements. Biomechanically, the neck functioned better as a structure extended in the horizontal plane than as a snake, capable of sharply curving upward or downward. The general anatomy of Albertonectes followed the typical elasmosaurid pattern: small head, extremely long neck, compact barrel-shaped trunk, short tail, and 4 large paddle-shaped flippers. The humerus was relatively slender, with a length-to-width ratio close to 0.56, and both front and rear flippers had flattened, overlapping phalanges forming broad, rigid, propulsive surfaces. The body was clearly designed for a swimming style based on underwater flight, coordinated beats of all 4 flippers rather than serpentine movements of the tail. Although the skull was not preserved, comparison with other elasmosaurids allowed inference of a narrow, elongated jaw with conical, fine, slightly backward curved teeth, ideal for capturing fish and cephalopods. The combination of a small head and very long neck fit a feeding mode in which only the front of the body was presented toward prey schools, approaching them with discrete movements and avoiding the turbulence that the trunk would have generated if moved directly. The sedimentary context of the bare paw formation indicated that Albertonectes lived in a relatively deep epicontinental sea, the Bare Paw Sea, the northern portion of the western interior sea. The sediments consist of dark shales and marls, with abundant remains of ammonites, bivalves, bony fish, and other marine vertebrates, suggesting open waters below the shallower coastal zone. In this environment, Albertonectes likely occupied a niche as a specialized pelagic predator, moving through midwaters and perhaps performing moderate dives, though its morphology does not suggest diving as deep as a robust ichthyosaur. The holotype skeleton also preserved a large concentration of gastroliths in the abdominal region, hundreds of polished stones ranging from small to medium. Later studies on their distribution and mass concluded that their total weight represented only a minimal fraction of the body mass, insufficient to function as significant ballast. Their main role would have been as a gastric mill, helping to grind prey swallowed whole, such as hard-scaled fish or relatively fragile shelled ammonites. From an evolutionary perspective, Albertonectes represented an extreme within Elasmosauridae. The diagnostic features noted in its description, such as the extremely high cervical count, the particular vertebral morphology, the absence of certain bony bars in the pectoral and pelvic girdles, and the presence of a fused distal tail section indicated a highly specialized lineage. The general trend in Cretaceous elasmosaurids was to increase neck length and reduce relative head size, but Albertonectes pushed this trend so far that it approached the functional limit. An excessively long neck would have compromised maneuverability and increased the risk of injury. The estimated weight of Albertonectes, according to recent volumetric calculations, was around 5 tons for an individual about 12 meters long. This mass, combined with a center of gravity near the trunk, required very precise control of neck position. Any abrupt movement of the head would produce considerable torque on the body, therefore it likely moved its neck relatively smoothly, making continuous adjustments rather than quick whips. Regarding reproduction and physiology, Albertonectes probably shared the same strategies as other advanced plesiosaurs. Evidence of viviparity in related plesiosaurs allowed inference that it also gave birth to live young in the water, without the need to return to land to lay eggs. Its metabolism, judging by dense bone structure and by analogy with other large marine reptiles, was likely relatively high, compatible with sustained activity in the temperate to cool waters of the interior sea. In the history of marine gigantism, Albertonectes occupied a unique place. It was not the heaviest or most massive, but it was one of the most extreme in terms of anatomical configuration. Its neck, which set an absolute vertebral record, illustrated how far specialization could go for capturing mobile prey in the water column without bringing the whole body closer. While it swam in the deep waters of the Bare Paw Sea, other long-necked elasmosaurids and robust mosasaurs shared the same sea, offering a marked contrast between two different solutions to the same ecological problem, being a large predator in an ocean full of fish and cephalopods. Thalassomedon, the lord of the sea of the early Cretaceous interior. Before Styxosaurus and Albertonectes reached their extreme configurations in the Campanian and Maastrichtian, another large elasmosaurid, Thalassomedon, had already explored the same evolutionary path in the mid-Cretaceous. The genus name, which can be translated as Lord of the Sea, aptly reflected its ecological role. It lived around 95 million years ago during the Cenomanian in the waters of the western interior sea, which were beginning to divide North America into two continental masses. Thalassomedon hanningtoni, the type species, was described from a relatively complete skeleton from Colorado. This specimen allowed an estimate of a total length of about 12 meters, with a neck reaching nearly 6 meters, composed of at least 62 cervical vertebrae. Compared with Albertonectes, it had fewer vertebrae in the neck, but still clearly belonged to the very long-necked plesiosaur category. The trunk was robust, the tail relatively short, and all four limbs were transformed into broad, flattened flippers, classic features of the elasmosaurid body plan. The anatomy of Thalassomedon fit a swimming style based on underwater flight. The front flippers were slightly larger than the rear ones and articulated with a broad pectoral girdle with scapulae and coracoids strongly fused, forming a kind of rigid, bony ring. This structure provided a solid base to anchor the flipper musculature necessary to generate powerful thrusts with each stroke. The rear flippers acted as stabilizers and also contributed to propulsion, but to a lesser degree than the front ones. The skull, although not as complete as in other plesiosaurs, was reconstructed as relatively small and narrow compared with the body. The jaws were elongated and armed with conical pointed teeth adapted to pierce and hold slippery prey. The dentition lacked pronounced cutting edges or large crushing teeth. Everything indicated a diet of fish and cephalopods, captured and swallowed whole rather than torn apart. The interlocking arrangement of the teeth fitting together when the mouth closed formed an effective grid to prevent prey escape. The cervical series of Thalassomedon was especially informative. Each vertebra was relatively low and elongated with articular surfaces allowing some flexion in the horizontal and vertical planes, but without reaching the extreme angles seen in many older reconstructions. Biomechanical studies on analogous elasmosaurids suggested that the neck did not rise in an S shape above the water, as was often depicted in the past, but remained mostly aligned with the body axis with gentle curves. In this framework, the neck functioned as a long-reaching articulated arm meant to position the head within a wide volume of water around the animal, rather than performing dramatic serpentine movements. The sedimentary context of Thalassomedon fossils in Colorado and adjacent areas indicated that it lived during a relatively early phase of the western interior sea. The rocks associated with its remains represented pelagic or subpelagic environments, with abundant ammonites, belemnites, and bony fish. This setting corresponded to a sea deeper than the coastal shelves, yet still relatively shallow on an oceanic scale, likely reaching depths of several hundred meters. In this environment, Thalassomedon would have acted as a mid-water predator, moving through the water column in search of schools of fish. The discovery of gastroliths in the abdominal region of some related elasmosaurids and Thalassomedon's association with this group allowed researchers to infer that it also used stomach stones. The primary function of these gastroliths would have been to aid in the mechanical breakdown of prey in the stomach, complementing the action of gastric juices rather than serving as significant ballast. In animals of this size, the weight of the stones represented only a small fraction of the total mass, insufficient to substantially affect buoyancy, but useful as an internal mill for processing scaly fish and shelled cephalopods. From a taxonomic perspective, Thalassomedon was placed within Elasmosauridae as a relatively basal member compared with later and more specialized forms such as Styxosaurus or Albertonectes. Its proportions already displayed a very long neck and compact trunk, but with some axial and appendicular skeletal traits less derived than in Campanian and Maastrichtian elasmosaurids. This intermediate position made it an important piece for understanding how hyper-elongated necks and the feeding strategies associated with them evolved throughout the Cretaceous. Ecologically, Thalassomedon occupied a specialized pelagic predator niche. The western interior sea during the Cenomanian hosted other large marine vertebrates, lamniform sharks, sizable bony fish, early mosasaur forms, and other plesiosaurs. Within this context, Thalassomedon functioned as a hunter of small to medium-sized prey, unlike the short-necked pliosaurs that focused on larger, tougher prey. Its strategy likely involved covering extensive areas, detecting and exploiting concentrations of fish and cephalopods in open waters. Thalassomedon's reproduction, although not directly documented, was inferred by analogy with other plesiosaurs to be viviparous. Evidence from plesiosaurs with embryos preserved within the body cavity, dating to similar periods, pointed to a general pattern of giving birth in water for the group. This implied fully marine life cycles without the need to return to land to lay eggs, enabling colonization of regions far from emergent coastlines. Thalassomedon represented a chronological and morphological link between early and mid-Cretaceous long-necked elasmosaurids and the extreme giants of the late Cretaceous. Tylosaurus, the giant mosasaur of the inland sea. While the long-necked elasmosaurids patrolled the western inland sea, another lineage of large marine reptiles reached comparable sizes, but with a completely different body plan. Tylosaurus was a giant mosasaur from the late Cretaceous, a marine lizard distantly related to monitor lizards and snakes that lived between 90 and 75 million years ago in the waters covering much of central North America. The first well-studied fossils of Tylosaurus came from the Niobrara Formation in Kansas, where nearly complete skeletons were preserved in the limestones and marls of the ancient inland sea. By the end of the 19th century, paleontologists such as Cope and Marsh described large mosasaurs with elongated skulls and solid snouts. Over time, these remains were reassigned to the genus Tylosaurus, whose name referred to the knob or bony protuberance at the tip of the snout, a distinctive feature that gave it a solid and reinforced frontal profile. In terms of size, Tylosaurus ranked among the largest known mosasaurs. The most famous specimen, a Tylosaurus proriger skeleton preserved at the University of Kansas and nicknamed Bunker, was estimated between 12 and nearly 16 meters in length, according to different reconstructions. Other Campanian skeletons indicated typical lengths of 13 meters for large adults. The oldest specimens from the Turonian and Coniacian barely reached 7 meters, showing a clear evolutionary trend toward increasing size over time. The anatomy of Tylosaurus contrasted sharply with that of plesiosaurs. It had a serpentine body with an elongated trunk, a powerful tail ending in a vertical fluke, and 4 limbs transformed into relatively short, wide flippers. The skull was large and narrow, with a solid snout projecting ahead of the tooth row. In proportion, the head represented about 14% of the total body length, a high figure for a marine reptile. Inside the mouth, Tylosaurus carried a battery of conical, sharp teeth, slightly curved backward, designed more for gripping and piercing than for cutting. As in other mosasaurs, in addition to the main row, there was a second series of teeth on the palate, which helped manipulate and swallow prey once captured. The feeding mechanism relied on a combination of a powerful bite and movement of the skull and upper jaw, with mobile joints that somewhat resembled those of modern snakes. Direct evidence of the diet of Tylosaurus came from several skeletons with preserved stomach contents. In 1918, Charles H. Sternberg recovered an 8.8-meter T. proriger skeleton in Kansas that contained partial remains of a plesiosaur inside. The discovery demonstrated that these mosasaurs preyed on other large marine reptiles. Subsequent investigations identified bones of smaller mosasaurs, bony fish, sharks, sea turtles, and even diving birds like Hesperornis inside various specimens. All evidence pointed to Tylosaurus occupying the apex superpredator level, capable of exploiting virtually any prey available in the inland sea. Regarding locomotion, Tylosaurus propelled itself mainly with its muscular tail, which ended in a vertical caudal fluke, functionally similar to that of a shark. The front and rear flippers acted primarily as stabilizers and rudders rather than the main source of propulsion. This pattern, derived from terrestrial ancestors with functional limbs, converged with the design of other large marine vertebrates that had similarly solved the problem of moving efficiently in water. The presence of skin impressions in some related mosasaurs showed small rhomboid keeled scales, which would have reduced water resistance during swimming. The environments inhabited by Tylosaurus corresponded to the western inland sea and other marine basins of the northern hemisphere. In North America, the inland sea was a vast oceanic corridor connecting the Arctic with the Gulf of Mexico, dividing the continent into 2 landmasses. Its waters hosted a diverse fauna of fish, sharks, seabirds, plesiosaurs, and other mosasaurs. In this setting, Tylosaurus occupied the top of the food web, above smaller predators like Platycarpus and Cledastes, and occasionally competing with other large mosasaurs. Research on Tylosaurus also included aspects of coloration and skin. Microscopic study of scales attributed to T. nepiolicus detected abundant eumelanin pigment, consistent with a dark coloration in life, possibly similar to that of the modern leatherback turtle. It was proposed that it may have exhibited a countershading pattern, with a darker back and lighter belly, a common strategy in large modern marine predators to camouflage both from prey and potential rivals. In evolutionary terms, Tylosaurus belonged to the subfamily Tylosaurinae within the family Mosasauridae. The lineage's history showed a progressive increase in size throughout the late Cretaceous, accompanied by specialization in using the reinforced snout to ram or locate prey. The coexistence of multiple species indicated that this type of mosasaur occupied a broad spectrum of niches across different stretches of the inland sea and other epicontinental seas. Shonisaurus, the Triassic colossus of Nevada and the Pacific. Long before giant mosasaurs like Tylosaurus dominated the Cretaceous, the oceans of the late Triassic had already produced true colossi. Among them stood Shonisaurus, an ichthyosaur of exceptional proportions that lived between the late Carnian and early Norian, about 210 million years ago, in seas covering what is now Nevada, the Pacific coast of North America, and adjacent regions. It represented one of the first instances of a marine vertebrate reaching lengths comparable to those of the largest later mosasaurs and plesiosaurs. The classic type, Shonisaurus popularis, is known from at least 37 incomplete skeletons found in the Looning Formation in the Shoshone Mountains of Nevada. These remains, systematically excavated from the 1950s onward, showed animals reaching 15 meters in length, with vertebrae up to 30 centimeters in diameter. The genus name precisely alluded to this geographic origin, Shoshone lizard. In 1984, S. popularis was adopted as the state fossil of Nevada, cementing its image as a paleontological emblem of the region. The anatomy of Shonisaurus displayed a combination of typical ichthyosaur traits and features linked to gigantism. It had a bulky fusiform body, with a deep and relatively wide trunk, generally similar in proportions to a large cetacean. The skull was elongated, with a long, narrow snout and pectoral and pelvic fins notably longer and narrower than those of other Triassic ichthyosaurs. This configuration indicated a powerful swimmer, capable of covering long distances in open seas but perhaps less maneuverable than smaller species. For years, Shonisaurus was interpreted as almost toothless, with teeth only in juveniles and absent in adults, leading to proposed diets based on suction or small soft prey. However, later discoveries indicated that it had teeth at all onto genetic stages, though not as robust as in other macro-predatory ichthyosaurs. Recent studies on dental morphology and stomach contents suggested it was a raptorial predator of large prey, capable of feeding on sizable fish, shelled cephalopods, and possibly smaller marine reptiles. The Nevada site, now protected as Berlin Ichthyosaur State Park, offered a unique view of Shonisaurus's life. Under the structure known as the Fossil House, numerous large skeletons were preserved at the same level. Modern investigations reinterpreted this concentration not as a simple, isolated mass mortality, but as evidence of recurrent aggregations of large animals with the presence of neonates and embryos over thousands of years. This demographic distribution, with an abundance of very large adults and a lack of intermediate juveniles, better fit a breeding or birthing area than a simple cemetery caused by random events. In paleoenvironmental terms, Shonisaurus inhabited a low-diversity tropical sea, relatively deep by Triassic standards, with bottoms dominated by fine sediments and a relatively limited accompanying fauna compared to the Jurassic and later Cretaceous seas. The repetition of skeletons in the same stratigraphic interval, some even overlapping, suggested that these basins functioned for a long time as gathering points for pregnant females coming to give birth, analogous to certain modern whale breeding areas. The gigantism of Shonisaurus was not limited to Nevada. In the northeastern Pacific, in the Albertonectes Formation of British Columbia, another species, Shonisaurus sicaniensis, was described in 2004 from an almost complete skeleton about 21 meters long, placing it among the largest known marine reptiles. Its classification sparked prolonged debate. Later studies proposed moving it to the genus Shastasaurus, while other phylogenetic analyses supported keeping it within Shonisaurus. Today, the discussion continues, but all agreed that it was an extreme ichthyosaur, comparable in size to a large rorqual whale. If S. sicaniensis is accepted as part of the genus, Shonisaurus ranged in size from the 15 meters of S. popularis to the 21 meters of the Canadian giant, with estimated masses of several tens of tons in the largest specimens. This scale placed it in competition with the largest mosasaurs and plesiosaurs in history, despite having lived more than 100 million years before them in a Triassic ocean just recovering from the Great Permian extinction. The morphology of the fins and vertebral column indicated that Shonisaurus propelled itself mainly by lateral tail undulation, probably ending in a well-developed vertical caudal fin, while the fins acted as stabilizers and control surfaces. The bulky body and robust tail musculature suggested an efficient cruising swimmer, capable of covering long distances and maintaining sustained speeds rather than performing sharp maneuvers. Its reproductive biology was inferred by analogy with other ichthyosaurs, viviparity, giving birth in the water, and relatively large offspring in proportion to the maternal body. The discovery of neonate and embryo bones in the Nevada concentration fit this interpretation and reinforced the idea that it used certain basins as recurrent breeding areas, implying migratory behaviors and some social complexity, or at least fidelity, to specific locations. In the history of marine gigantism, Shonisaurus held a key place. It demonstrated that just 20 million years after the Permian mass extinction, marine vertebrates had already reached sizes comparable to the largest Cretaceous reptiles. Its bulky body, elongated skull, and narrow fins constituted an early and efficient solution to the challenge of dominating the open oceans. Mosasaurus, the lizard of the Meuse and emblem of the Cretaceous seas. Among all marine reptiles of the late Cretaceous, Mosasaurus held a privileged position both for its size and its historical significance. It was a large mosasaur that lived approximately 83 to 66 million years ago during the Campanian and Maastrichtian, in seas covering broad areas of Western Europe, North America, and the emerging Atlantic. Its name, Lizard of the Meuse River, referred to the location where the first remains were found, quarries near Maastricht in the Netherlands at the end of the 18th century. The study of these fossils by Georges Cuvier became one of the foundational milestones in vertebrate paleontology, convincingly demonstrating the existence of extinct species. Mosasaurus was a highly derived mosasaur, fully adapted to marine life. It had a streamlined, relatively robust body, with an elongated trunk, a laterally compressed tail ending in a bilobed caudal fin, and 4 limbs transformed into flippers. The discovery of a related mosasaur with preserved soft tissue outlines confirmed that advanced mosasaurs propelled themselves primarily with a powerful vertical tail fin, functionally comparable to that of a shark, rather than a simple pointed tail as reconstructed in the past. In terms of size, the most emblematic species, Mosasaurus hoffmanni, ranked among the largest known mosasaurs. Although a complete skeleton remains incomplete and much of the estimates were based on isolated skulls, classical studies relied on an approximate 1:10 proportion between jaw length and total body length. A Russian specimen with a lower jaw of 1.71 meters led to maximum estimates around 17 meters in length for some individuals. Later work considered these figures likely somewhat overestimated, but agreed that Mosasaurus reached at least 15 meters, with the largest specimens approaching the upper limit of that range. The cranial anatomy reflected its role as a super-predator. Mosasaurus had an elongated, robust skull with deep jaws and a row of conical, slightly compressed, backward-curving teeth. In addition to the main dentition, the palatal vault carried a second row of teeth, a typical feature of mosasaurs. This double system allowed it to firmly grasp prey and move it toward the esophagus through alternating movements of the skull and jaw, in a manner analogous to modern snakes. Stomach contents and remains associated with mosasaur skeletons allowed reconstruction of its diet. In the case of Mosasaurus and related genera, large bony fish, sharks, ammonites, sea turtles, plesiosaurs, and even other mosasaurs and seabirds were documented. Recent studies of dental microwear and geochemistry also showed that Mosasaurus occupied very high trophic levels, distinct from other mosasaurs like Prognathodon or Plioplatycarpus, confirming its apex predator position in many Maastrichtian marine ecosystems. The locomotion of Mosasaurus relied on lateral tail undulation, equipped with a well-developed vertical fin, while the fore and hind flippers functioned primarily as stabilizers and maneuvering surfaces. The presence of small, overlapping scales observed in mosasaurs with preserved skin suggested a relatively smooth body surface, optimized to reduce water resistance. Overall, its body followed a recurrent pattern in large marine vertebrates: fusiform trunk, propulsive tail, and limbs converted into flippers, convergent with ichthyosaurs and early cetaceans. From a paleobiogeographic perspective, Mosasaurus appeared mainly in Maastrichtian deposits of Western Europe, such as the Maastricht limestones and related areas of the North Sea basin, but attributed remains or teeth have also been found in North America and Northern Africa, indicating a probably pan-Atlantic distribution. In these basins, it shared the seas with other large mosasaurs, turtles, bony fish, sharks, and late Cretaceous plesiosaurs, forming part of marine communities among the most diverse of the Mesozoic. The reproduction of Mosasaurus is inferred by analogy with other mosasaurs and marine reptiles as viviparous. Mosasaurs related to embryos preserved within the body cavity are known, demonstrating that these animals gave live birth in the sea and did not bury eggs on beaches. This implied fully marine life cycles, with the possibility that pregnant females moved to relatively protected areas to give birth, although no breeding grounds as clear as those documented for some Triassic ichthyosaurs are known. Historically, the importance of Mosasaurus went beyond anatomical aspects. The Maastricht specimen, even contested as war booty in the 18th century, was studied by Cuvier, who concluded that it belonged to an extinct marine reptile and not to any living animal. This reasoning decisively supported the concept of mass extinction of faunas and paved the way for the development of paleontology as a science. From then on, Mosasaurus became a classic reference in museums and popular works, although for much of the 19th and 20th centuries it was depicted inaccurately, resembling a partially amphibious lizard. Only with the discovery of soft tissues and comparative analysis was the current image of a fully oceanic apex predator consolidated. Mosasaurus represented the late culmination of the large mosasaurs model. It coexisted with related forms of similar length, such as Tylosaurus, and shared with them dominance of the seas during the final millions of years of the Cretaceous. With the mass extinction at the Cretaceous to Paleogene boundary, both Mosasaurus and other mosasaurs disappeared along with non-avian dinosaurs and many other marine groups. Shastasaurus, the giant specialist of the Triassic seas. Shastasaurus was not only a large ichthyosaur of the late Triassic, but also one of the most extreme representatives of a specialized branch within ichthyosaurs, the Shastasaurids, which included forms ranging from 6 to over 20 meters in length across different Triassic oceans. The genus was originally described from fossils from the late Triassic of California. The type species, Shastasaurus pacificus, is known from remains found in Shasta County, giving the genus its name, the lizard of Mount Shasta. It was a medium-sized ichthyosaur within the group, with an estimated length exceeding 7 meters, although some fragmentary specimens suggested slightly larger dimensions. Its anatomy already showed the distinctive traits of Shastasaurus: a slender body in profile, a relatively narrow trunk, and a skull with a short snout compared to the more typical long-snouted ichthyosaurs. Over time, other specimens were discovered along the Pacific coast of North America and in southern China. In Guizhou province, a species initially assigned to Guanlingsaurus was later reassigned to Shastasaurus liangae. This exceptionally complete material showed an animal about 9 meters long, with a particularly short skull and practically toothless. It only retained tiny teeth, and in some adult individuals not even that. This combination of a reduced snout and absence of robust teeth set it apart from classic large fish predatory ichthyosaurs, which had long jaws with powerful dentition. The cranial morphology of Shastasaurus liangae led to the proposal that it was a suction-feeding specialist. Detailed study of its skull revealed a compressed face, retracted nostrils, and a broad space for soft tissues around the mouth, traits reminiscent of certain modern odontocete cetaceans. Based on this, it was interpreted that this ichthyosaur primarily hunted soft-bodied cephalopods and small fish, which were rapidly sucked in by the sudden expansion of the oral and pharyngeal cavity rather than captured with biting. However, the specialization of Shastasaurus was not explained solely by the skull. The shape of the body was also distinctive. Unlike other bulky ichthyosaurs such as Shonisaurus, Shastasaurus had a relatively slender trunk, with ribs forming a chest less deep than expected for its total length. In the largest Shastasaurids, the distance between the pectoral fins could exceed 7 meters, but the thoracic depth barely reached 2 meters, giving a narrow lateral profile. This configuration suggested an open-water swimmer, with a body optimized to reduce resistance and maintain efficient cruising speeds rather than execute sharp maneuvers. A key issue in the history of Shastasaurus was the question of maximum sizes. In the Pardonet Formation of British Columbia, a giant ichthyosaur about 21 meters long was described in 2004, initially assigned to Shonisaurus sicaniensis. Its size placed it among the largest known marine reptiles. Later studies suggested it was more closely related to Shastasaurus than to Shonisaurus and reassigned it as Shastasaurus sicaniensis. More recent phylogenetic analyses, however, realigned it with Shonisaurus, forming a small separate clade. The debate continues, but in any case, this material demonstrated that Shastasaurids, broadly understood, included forms that rivaled in length the largest Mosasaurs and Pliosaurs that appeared later. Regarding locomotion, Shastasaurus shared with other ichthyosaurs a swimming mode based on the tail. The skeleton indicated a heavily ossified vertebral column in the caudal region, capable of supporting a well-developed vertical fin. Propulsion was generated by lateral tail undulation, while the relatively broad pectoral and pelvic fins acted as control and stabilizing surfaces. The long, narrow body, with a cross-section less massive than that of Shonisaurus, was consistent with a long-range swimmer, capable of covering extensive areas of open sea in search of cephalopod schools. The ecological context in which Shastasaurus moved was that of the late Triassic seas, a world still recovering from the Permian mass extinction. The basins where its remains appeared, both along the Pacific margin of Laurasia and in southern China, corresponded to marine platforms and slopes rich in ammonites, conodonts, and other pelagic invertebrates, but with vertebrate diversity lower than that observed later in the Jurassic and Cretaceous. The specialization of Shastasaurus towards soft-bodied prey was interpreted in some studies as a response to particular environmental conditions, including possible atmospheric oxygen minima and changes in the availability of different types of prey. Not all researchers agreed with the extreme suction feeding model. The analysis of certain elements of the hyoid skeleton, the bones supporting the tongue and associated musculature, suggested that, at least in some Shastasaurids, these structures were too slender to withstand the forces required for very powerful suction, opening the possibility that they combined moderate suction capture with ram feeding, similar to some cetaceans that actively pursue their prey. In any case, the general consensus recognized that Shastasaurus diverged from the classic model of a toothed ichthyosaur that hunted large fish with violent bites. From an evolutionary standpoint, Shastasaurus was placed within the family Shastasauridae, along with other giant, elongated ichthyosaurs such as Dinosaurs, ichthyosaurs, and Shonisaurus itself, depending on the classification adopted. This family demonstrated that the first major wave of marine gigantism in the Mesozoic was not linked to mosasaurs or plesiosaurs, but to Triassic ichthyosaurs, which occupied a wide spectrum of ecological niches, from raptorial predators to specialists in soft-bodied prey. Regarding its biology, Shastasaurus shared well-established traits with other ichthyosaurs: viviparity, air-breathing, and a fully marine life cycle. Although embryos have not been directly described for the genus, the presence of young in other ichthyosaurs of similar size and age makes it very likely that it also gave birth in the water. Its bone growth patterns, derived from histological studies of related Shastasaurids, indicated high growth rates during juvenile phases, necessary to reach adult lengths exceeding 10 meters within a relatively short geological time. Shastasaurus represented the Triassic extreme of specialized gigantism, while Shonisaurus embodied the model of a bulky colossus likely preying on relatively large animals. Shastasaurus showed how a marine lineage could achieve similar lengths with a more slender body, and a diet focused on soft-bodied prey captured very efficiently. Millions of years later, mosasaurs like Mosasaurus and Tylosaurus, and plesiosaurs such as Pliosaurus or Albertonectes would explore other paths to gigantism, with massive skulls, interminable necks, or serpentine bodies. All of them, however, in some way followed the path already opened in the late Triassic, when ichthyosaurs like Shastasaurus first demonstrated just how large a predator could become in the oceans of the planet.